All right. So I don't know if you have a favorite Disney Pixar movie, but Inside Out was actually the first one ever touch my heart because you always have a like sometimes we do feel like okay, I want to be happy all the time, but without those sadness thing, you won't feel happy because like if you are better or worse, it's just because you compare, right? So because we have those sadness situations, so we know how lucky we are right now, and we value where we are, right? And as I said, like in the learning curve, right, we typically would remember what we suffer the most, which is very surprised, right? So, and I think those are the things that Inside Out have been telling us. And another thing that I want to say, like today, starting today, we are going to talk about a topic called memory hierarchy. And the reason why we talk about memory hierarchy, I will explain that later. But this is definitely one of the part that I promise that everyone got lost in their undergrad study in computer architecture. No one ever showed me they understand memory hierarchy very well, even though they got an A+ in undergrad computer architecture. So please pay attention to the following 5 lectures regarding memory hierarchy. If you don't pay attention to those, I'm sure you will get lost in there. And if you want to watch Inside Out movie, as we know, like get Disney Plus, and also like for later on they have the Inside Out 2, and it's also on Disney Plus, I believe. And I don't receive any money from Disney these days. Well, I never receive money from them. And hopefully after they see this YouTube video, they will consider doing something. And now, but before that, let's go back to where are we coming from? So, I always like to start with the big picture, no matter it's in research or in life or in teaching. And don't forget, our big picture in computers is von Neumann architecture, which means that our computer has this main components, processor, memory, and storage. And the way how we use processor and memory is that if a processor needs to execute a program, it always requires the program itself and the data present in the memory before the processor can do anything. And then inside that processor, there's a special register called program counter, tells the processor where in a memory should I fetch the next operation, next command to run. And then once we got that from the memory to the processor will start looking into what the instruction really want us to do and prepare the operands and select the right LU for computation. And once we are done, we advance to the next instruction. So as you can hear, right, memory is so important because a lot of people would think processor know what to do next. I will tell you, processor doesn't know anything until it got something from the memory, right? So and also memory is where really makes von Neumann architecture valuable, because without memory, your computer, your processor can only perform fixed functions. However, with the concept of memory, you will be able to let the computer change its combination of the functionality because you load different content into the memory. So I would say memory is actually the soul that really make von Neumann computer architecture different from other counterparts at the same time. And why are we starting with memory? So a lot of undergrad computer architecture, I think they have the wrong order. They typically start with pipeline processors, and then people start to hate computer architecture, isn't it? Right? How many of you have that kind of undergrad computer architecture? You start performance simulation, talk about 5-stage MIPS pipeline, and then you feel like, okay, this is not my thing, right? So today, we want, as a grad textbook, they also start with the memory, and there is a reason why. After we learn the performance equation, and after we learn the M-Gauss law, it tells us that we should start with the most common case, right? And I will show you that the most common case is indeed memory instead of processor. So, but before we talk about that, I want to ask you a question that is somewhat related to what we are going to teach today. What percentage of English words from the dictionary do you think someone has to know for their everyday life? Grab a few people around you, talk about that. All right, do you guys have a conclusion? Sounds like you guys become quiet so quick. How many percentage of English words do we have to know every day? 2.5%. How did you get that number? Because you looked it up online? No. Oh, you heard it before? No. Okay, but why? But 2.5 sounds like a very precise number. Uh-huh. If so, then maybe I can't imagine this was more than 250. Okay. Okay. Other answers? 2.5%? Somewhat like that? Okay. So, like, it's very interesting. So, like, as a faculty member, right, I always, like, look into those, like, grad school applications. And one thing I've never looked into is actually GRE. Because, like, as a formal international student, right? Like I went through that process of preparing GRE. And then like, well, I have like several years of English education before taking GRE. And then when I took the GRE, during the preparation process, I just feel like, no, this is not the set of word that I would use every day. And then I'm surprised that, there are this set of words existing ever in the world, and somebody is still using it, right? So when I recruit students, one thing that I forgot to watch is always the GRE, and it's kind of like ironic. There was one student that I want to recruit from South Korea, and then before I sent out that admission, the school sent me a notice saying that, your student has a very low GRE. Are you sure you want to admit that student? And I said, well, I can talk with him without any problem, right? So, but it turns out that I have to write like several hundred words as an excuse why we can make an exception for that student. But here's the thing, right? My personal experience tells me that it's not going to we are not going to use a lot of words. And in reality, right, like the world has a lot of different things. And in reality, like English words or every conversation is not the only thing that represent, although we have a lot of things existing in the world, but most of the time we only use very few amount of them. So one of the example is actually regarding the money, right? So like you will be surprised, like top 10% people in the world, they own 67% of the wealth in the United States. And I'm also surprised, and so like, okay, the rest of 90% of people only own like 33% of the wealth in the United States. And I can tell you I'm not on the top 10%, because based on a study in the greater Los Angeles area, my salary, if you are interested, you can definitely look it up online, because all the state employees, our salaries are available online. So I don't want to tell you where you can find it, but you can Google it, right? So for my salary, I am not on the top 10%. I'm somewhere around like 20%, but not 10%. And so like how rich these people they have to be, and they own 67%, right? And like in computer science, right? So that's on the social science side. In computer science, there is also a famous 80-20 rule by Microsoft saying that, like 80% of the errors and crashes in Windows caused by 20% of the entire pool. And there's always like, and there's also like 80% of the end users generally use 20% of the features, right? So you implemented a lot of features, like how many buttons in Office, Microsoft Office, that you have never touched? I bet there will be a lot, right? So 80% of the users only use 20% of the features. How about our words? So native English speakers use around 2,000 to 3,000 words in daily life. So a little bit more than a lot more than 1,000, right? But even with that, like 2,500 to 3,000 words, you can understand 90% of everyday life conversation. So that's why I was like telling everybody that don't look at GRE, right? Like TOEFL, I think it makes sense for international student, but for GRE, really, you're testing that remaining 10% of the words to judge if these people can enter the grad school. Seriously, right? And okay, but based on that, right? If you check the Oxford English Dictionary, there are 1,700 words, right? So if you compare that, you only need to know 2% of the English words to understand 90% of the conversation. So that's why I'm asking you why you have that 2.5% is very close, right? So 2% of the English words, you can understand 90% of the conversation. So you might wonder, why is it related to what I'm teaching today? So today we are going to start with the memory wall problem, and then we are going to talk about the predictable code behavior and designing the cache in a way that we can capture that predictable behavior. So why are we starting with the memory part? Because if you take a look of the latency between the processor and memory, so this is the real data that I plotted using the real data that you can get from public sources. So in DRAM, there are typically some kind of standard teaching people that if you want to manufacture a DRAM module, how fast it has to be. And typically, when you manufacture the DRAM, you don't want to go over that because it's just wasting my money, right? And also the other thing is that the memory controller doesn't support it. And the reason why they need a standard because the memory, the CPU and memory, as you can see, they are highly correlated in the von Neumann architecture. So they have to be synchronized. So if you want them to be synchronized, it cannot use some kind of like a network protocol styles protocol to communicate with each other. They have to be clock by clock, use a synchronized protocol. So that means that the timing matters. And in the meantime, I'm also plotting the frequency of the processor at the same year the standard was released. And as you can see, the latest standard is called DDR5. And at that time, the frequency of your CPU is already driven down the latency pretty low. So nowadays, we typically have a 2 gigahertz or 4 gigahertz processor, which means your latency can be as low as 0.25 nanosecond. But in the meantime, if you check the latency of your DRAM, it's actually close to somewhere like 13 to 14 nanosecond in the best case. What do I mean by the best case? Because there are several different steps in DRAM access. And one of the steps is code. So there are data lookup, and there is also like filling the page buffer. And what the latency I'm citing here is assuming that everything is already in a page buffer. So that's the best latency the DRAM can give you their data. So even with that situation, it's still around 37 something more than the CPU time, right? So what does that mean is that there's a huge performance gap between your processor and memory. So now some people might think, does that really matter to you? So can you go through this problem to see how serious that problem is? All right, let's take a look. Okay, so we see somewhat diverse answers. So why don't you guys discuss with each other and see which is more likely the right answer? All right, let's take a look. After discussion, this is what do you guys think? Okay, so now more of you think it's C and a lot of you think it's B. Okay, this proves one thing. As I mentioned, I haven't seen anyone ace in computer architecture, but they really understand memory hierarchy. So neither B or C are right answers. So is right answer. So what's the average CPI? So first of all, in the very beginning, we have been talking about the volume architecture, right? So what's the very first step of executing a program? Loading it into the memory. And then how do I start an instruction? Loading it into the register? With a program counter. And why do I need to use a program counter? Okay, that's one purpose. What's the other purpose? What's a program counter? What? Okay, to fetch the instruction. So a lot of people think the program counter is like a counter of instruction lines. That's actually wrong. The program counter, in fact, it means the memory address of your instruction. So the program counter is telling us where the processor should fetch that instruction from the memory. What does that mean?
You need like an access to memory on every.
Okay, so every instruction would have at least one memory access. If it's a data load store instruction, then you would have an additional one or two, depending on what type of instruction is that. But let's say if that's one, right? So for data loading store instruction, there will be two memory access. But every instruction would have at least one. So does that change your mind? Right? So first of all, in computer architecture, because your processor and memory, they are synchronized. So everything has to be counted in CPU cycles first. So a lot of people, they got the answer wrong in some kind of performance evaluation because they always use the nanosecond directly to evaluate the performance. But I'm going to tell you, if you do that in your assignment too, your auto grader will tell you you're wrong everywhere, right? So what you have to do is that you have to convert the memory access time into the CPU cycle time, CPU cycles. So if I give you a 4 gigahertz processor, it means that your cycle time is 0.25 nanoseconds. So each DRAM access will cost 55 cycles. And as you can hear, right? So the average CPI for having no memory access at all is 1. But again, don't forget, you have to fetch an instruction from the memory. So every instruction, 100% of the time, I have to pay 55 cycles to just fetch the instruction. And then 20% of the instruction, they have additional 50%. So turns out it would take 67 cycles. So it's not B, it's not C, it's not even D. It's actually E, right? Everybody forget there is an instruction needs to be fetched from the memory. Okay, so if you count that in, the real instruction execution is only taking 1 cycle. The 66 cycles here, they are actually in memory. That translates to 98.85% of the time in execution. Why don't we start with this one, right? So a lot of people, they think the key issue of making the processor powerful fast is that we should have the best microarchitecture to make it faster. But I can tell you, that's actually not true. Whoever has the best memory hierarchy has the best processor. And that's why people, like a lot of companies, they are working on processors right now. But I can tell you, no one has done a better job than Apple. Because Apple really highly optimized their memory. And the same thing for x86 processors, like Intel and AMD. There is always some, if you pay attention to the microarchitecture of AMD, they did nothing wrong on the processor side. But the thing is that because they don't manufacture the memory in their fab, which is not tuned for the processor design. So their memories are slow. Their memory are very, very slow. So that's why Intel processor is always better, even though their cache size is not as big as their competitors, even though it seems like their microarchitecture does not using some fancy features as AMD or Apple use. But their processors are faster because memory, 98% of the time. And to be honest, I'm underestimating that number. If you pay attention to, in your textbook, there's a table showing that how many percentage of instructions are in memory accesses, and it actually shows you 35. So what does that mean is that the actual number of memory accesses or the actual percentage that we spend in memory access should be very close to 99 or even 100, right? So under that situation, any computer architecture class, as I mentioned, should start with the memory. And so based on that, right, we want to make the common case fast, and the common case is indeed the memory. So the very first takeaway is that a lot of people would think, okay, if I want to make my computer faster, I should buy a better processor, or I should use a faster GPU or whatever. But before that, how much time you spend in memory, right? Think about this question, right? Okay, so a lot of people will think, okay, can we address this in pure hardware solution? Just make the memory fast. And if you pay attention to the memory technology, yeah, there are faster memory like SRAM. But if you pay attention to the cost, it's 50 times more than the DRAM. What does that mean? So let me give you a real number, right? So right now, if you want to buy like a 64 gigabyte memory module, the cheapest that you can find on Amazon is probably around 100. So 50 means if I want to buy 100 sorry, 64 gigabyte of the DRAM, SRAM, and if it's available, I have to pay 5,000. That's more expensive than an NVIDIA RTX 5090. Actually twice, so you can buy two 5090s if you replace your DRAM as SRAM. Are you going to pay for that? Right, so we are not going to do that, right? So the thing is, we find an intermediate solution. And the intermediate solution is that we build memory hierarchy. So what does that mean by hierarchy? First of all, several things. By hierarchy, when you hear about a hierarchy, what's your feeling about hierarchy? Saying that a company is a hierarchy. When you have an issue, who do you report to? What? The person right above you, right? You're a manager, right? Are you allowed to talk to your manager's manager? Typically not a good thing to do, right? Because you are bypassing it, that's not good. So the same thing as hierarchy is that we build a hierarchy like that. So before we ask DRAM, I add a small unit called SRAM cache. CACHE is pronounced the same as CASH. So that's why I put a $sign here. Question?
The manufacturers put like some amount of RAM and maybe SSD inside the CPU.
They can do that too, but because of the limitation of the technology, their access time is always slow.
This communication.
What? Yeah, but the thing is that, okay, if you pay attention to the hardware technology that DRAM uses, it's charge-based. It's capacitance, right? So every capacitance has its own limitation on the access time. Make sense? So even though I put it on the CPU, it's not going to affect the time, the latency you need to spend. Does that answer your question? Okay, so we put SRAM caches inside your processor. So what does that mean is that before, every time when I want to access data, I would go through SRAM first. And if SRAM doesn't have it, then the memory controller associated with the SRAM will go look up for me in a DRAM. And if DRAM doesn't have it, we will go to storage. So in this way, it's a strict hierarchy. So one thing that you have to remember, with that hierarchy, it means that your processor do not talk to the DRAM directly anymore. It only talks to the top level SRAM cache that we have. And this is pretty much like what happened in Inside Out, right? Like they have the core memory, they have the control center. So you can imagine those registers are like this memory balls near their control center. And if they really need some short-term memory stuff, it's actually right behind the wall of the control center so they can get it really quick. And most of the time, right, except for during the movie time, when I want to grab a memory that's stored in a longer-term storage like DRAM, they would have a pipe that would put the stuff into this control center, but they don't directly go outside. Right? The reason, if you pay attention to that movie, the reason why it doesn't go outside is because something goes wrong, right? But most of the time, you don't go outside. They would send the stuff if it's not there, right? So that's why I'm saying this movie is highly related to the memory, right? A lot of people think about it as a psychological movie. It's about the neuroscience, but as a computer scientist, the first time I watched it, I was like, yeah, this is the movie talking about memory hierarchy. Anyway. The typical size of your SRAM is typically just like kilobytes to megabytes. And the size of your DRAM is pretty much like gigabytes nowadays and terabytes for storage. And if you pay attention to the latency, the register is pretty close to, it's pretty much aligned with the cycle time because the reason why we want to register is because it's going to be where the instruction want to work on. And for SRAM, it still takes a few nanoseconds. So in your assignment, you will experience how much time is that. And then in the DRAM, it's going to be tens of nanoseconds. So like the 13.75, that's a real number that I have for you. And most of the time, you're not going to be that lucky. So in a worst case scenario, it could be hundreds of nanoseconds. And for the storage, even though you are using the flash memory, or even though you are using like a phase change memory, it's going to be at the microsecond level. So now, why adding this small amount of cache is a good idea, right? So remember we said you only need 2% of the word to know 90% of the everyday life conversation. So in that case, let's assume we can catch 2% of that kind of stuff and know 90% of the workload. So in that case, what's the average CPI now? All right, let's take a look. The initial guess show that more than half of you think the answer is B, but from our experience in the previous question, you know, like sometimes majority, they are wrong, right? So why don't you guys talk with each other to confirm that this time majority is right? All right, let's see what you guys have. So after discussion, okay, 65%, so getting higher. So first of all, remember we have a memory hierarchy. So every time the processor has to ask L1, and then if L1 doesn't have it, then we will go to DRAM, right? So based on that, how do you guys get the answer that's B? How do we start with this question? What do you guys think? How to solve this problem?
Well, just based off the previous pull-up, we had to switch the 13.5 nanoseconds into cycles. So I switched the 0.5 nanoseconds into cycles as well.
So this is like 55 cycles after the switch. And how about this?
I got 2 cycles.
2 cycles. Okay. So this is two cycles, right? So based on that, now how do we use these numbers to get our result? So how many cycles we have to pay if we have a cache, if something is in a cache? 2. How many cycles do we have to pay if something is in a cache? 2? 3, right? Because we still have to execute the instruction, right? And that's only for instruction access, right? How about data? If the data is also in the cache, then 1 plus 2 plus 2, right? So, okay, but what if that's not in there? How many cycles? So it's a memory hierarchy. Before asking the cache, you have no idea if it's in there, right? So what does that mean? You have to go through the cache first, right? So 1 cycle execution plus 2 cycle access the cache, and then 55 cycles of accessing the DRAM, right? So what does that mean is that, first of all, we have the right start, the cycle time of each, right? And then for L1, if you are unfortunate about that 10%, right, you have to pay additional 55 cycles, right? So with that, you can put the answers like that. First of all, don't forget there is a cover fee when executing an instruction, right? 1 cycle. And then 100% of the time, I have to access the instructions. And if I'm lucky, I have 2, right? If I'm unlucky, I have to pay additional 55. And 20% of the time, I need to additionally access the data. And for this 20% of the time, again, if I'm lucky, I pay 2. If I'm unlucky, I'm paying additional 55, right? And don't forget, we always have this base 1, right? Okay, so based on that, you get an answer of 10. Okay, so now let's take a look. How do I know how big is my cache in my processor? So there are several ways that we can know. And on Linux, you can try this. So first of all, you can have an LS CPU, which would tell you the model number, and it would get you the configuration. And so let's take a look at that. So again, this is a user space application that like people wrote, and it's not always give you the right number. So like here you see like, okay, there's some parameter that are missing, right? So if you see that's the case, it means that this tool is not trustworthy. So if that's the case, right, then what you have to do is you might want to use a more fancier way, like grep. And in Unix abstraction, everything is a file, including hardware. So this is the file descriptor of the processor's cache. And the reason why in modern Intel architectures, we cannot get the cache size right is because they have the big little architecture. We will talk about that later towards the end of the quarter. However, the best way of getting the cache configuration nowadays is very ugly in a way that you have to manually grab the detail of the file descriptor and the hardware descriptor. And it will show you like, okay, like here we have the index 0. And it will tell you this is a cache with 64 number of sets, weights of associativity 12, and it's a data cache. So this is a cache for data, and its size is 48 kilobyte. And this is a level 1. Okay, and if you go through that, you will see there is also a A-weight associativity instruction cache, 32 kilobyte, and level 1. However, there are more. Like here, we have 2 megabytes unified cache with level 2, right? And people nowadays, like people even have more, right? Like this one, level 3, and it's 33 megabyte, right? So, okay, so it sounds like it's getting more and more hierarchical, right? And the same thing is that if you pay attention to what the LS CPU and the getconf give you on an ARM processor that provided by NVIDIA, right? So this is an NVIDIA Tegra Orin processor, the same one that used in your Tesla if you have one. So for this processor, you will see everything is like 0. So you know, like this tool is not convincing anymore. However, in your assignment, we are going to use this traditional tool because the processor generation there is well established. And but if you use this tool, it will give you the right number. So for NVIDIA Tegra, there is level 1 data cache 64 kilobytes, larger than the Intel, right? But the thing is, I told you, this process is going to be slower, even though it has bigger cache. And the instruction cache is also 64 kilobyte, twice the amount of Intel, right? And if you pay attention to index 2, right, they also have like level 2 cache 256 kilobyte and level 3 2 megabytes. So it looks like no matter Intel or NVIDIA or even AMD, nowadays your processor has multiple layers of caches. So why are people, so in fact, in reality, nowadays your memory hierarchy is more complicated in a way that the level of SRAM caches is not just one level. You have 3 levels of memory hierarchy. So it's pretty much like, okay, like in the past, right, in your company, when it's small, it's only like manager, big boss, and you, right? And now, like if you are working in a company like Google, like there will be like, you start with L3 and your manager is probably somewhere like L5. And then you talk and your manager will report to another manager, and then his manager or her manager or their manager will report to another manager, and then the manager will report to a VP, and then, well, if you're lucky, sometimes there will be more managers in between. But right now, because they lay off a lot of like this middle class, so I think it's going to be sing a little bit. But let's say the normal case, right? You don't talk to anyone as a president or even as a VP. And in the middle, you have a lot of like middle layers, right? So the same thing as the memory hierarchy here. So why are we doing more deeper memory hierarchy? How does that help? All right, let's take a look. So, okay, I love this answer because it means that we need some discussion. So why don't you guys discuss with each other? All right, let's take a look. Okay, after discussion, it's either A or B, but more of you are right now satisfied with the answer B. So can we have someone showing us how to solve this problem? Like, how do we start with? Okay.
Okay, so
What's your name again?
Kelsey.
Kelsey. Okay.
So last time we figured out that 0.5 nanoseconds is 2 cycles.
Mm-hmm.
So this time we're going to figure out that 5 nanoseconds is
20.
Is it? I think it's 20 cycles.
Right.
So 100% of the time we have to go into the L1 cache, which is 2 cycles,
Mm-hmm.
and then the that's going to work for 90% of the time, which means 10% of the time, which is 1 minus 90%.
Mm-hmm.
It's going to hit L2,
Mhm.
which is 20 cycles,
Mm-hmm.
and then of that 10%, it only goes into the final level 60% of 10%.
Right. So if you put that all together, it's going to give you an answer like 8 cycles or something, right? So it's closer to 10, right? Don't ask me why it's closer to 10, right? But it's closer to 10. So remember, previously we have an answer of 10. Adding more memory hierarchy does bring it down. But as you can see, it's not going to be as significant as what it used to help in bringing down the latency anymore, right? So that's why a lot of people might have the question, okay, if having a hierarchy is so great, why don't we add L4 in our processor? Everyone is kind of like satisfied with L3 right now. And the answer is that it's not that helpful after you add more levels in a hierarchy, right? So that's why when they lay off people in a company, they would rather like lay off people in the middle class because they don't do real job, right? But what really means is that nowadays we have a limited level of caches, and that's already good enough. So now the question you might have, the big question you might have, right, is that, okay, professor, you showed me it's so effective because you told me there's going to be like 90% hit rate. Are we able to achieve that 90% hit rate? So first of all, right, before we go into there, here are the second takeaway. Hierarchical caching with small amount of SRAMs will work if we can efficiently capture data and instructions. So can we really effectively capture the data or instructions we need, right? Then it turns out that it really means to another question is that, is your code behavior predictable? So this is the same problem that the same AI inferencing problem that we had at the last time. And the fully connected operation, as we show here, is in fact matrix vector operation. So here's the typical code of matrix vector operation. So can you show me, can you dig into the code and think about, in terms of locality, how good are them? All right, let's take a look. So, okay, we have this very diverse answer. So why don't we discuss with each other regarding what kind of locality do they exist? Are they existing in the code? All right, let's take a look. Okay, after discussion, 50% of you think the answer is E, which is great. So, first of all, tell me, what is spatial locality? What is spatial locality? Okay. Okay, so I would say that spatial locality means that the tendency that we would access or use neighboring items in the memory locations, right? So that's spatial locality. What about temporal locality? Okay, you are going to use the same thing for more than once, right? So that's the tendency of that. So that's pretty aligned with our everyday life, isn't it? Like one of the grocery store who didn't give me the money for this class is actually Ruff's. and I like to go with them because I like the way how they laid it out. Because every time when I go to get some sauces, they always put the sauces, the type of sauces that I like together. So for example, like if I'm doing pasta today, right, they would put like those pasta sauces that with different flavors in like neighboring racks, right? So this is, so you, when you go by it, it's just like grabbing it, right? So that's spatial locality. And you know, like once in a while you would need the same sauce. And if you have a flavor or a brand that you like, it's very likely you are going to purchase it again, right? That's temporal locality. So based on that, who in a code has spatial locality, meaning that we are going to access the neighboring item after we are done with the previous one? What? The matrix? The vector, right? So if you pay attention to the loop index j, they will increment one by one, right? And based on the allocation in the memory, it's sequential, and that means they are in a neighbor. Okay, so is matrix vector the only one who has the spatial locality? Who else? Output also have spatial locality, right? Because you go do this I++ all the time. Okay, who has temporal locality? Vector. Why do we have temporal locality on vector? Okay, so when we increment I, even though the I is changing, we are going to access the same j again in a code. That's temporal locality. Do we have temporal locality on output? No, because we only traverse the same I once. Do we have temporal locality on matrix? Because every time ij is different, right? So for this piece of code, we know that, okay, no matter what type of data structure we have, they at least hold one type of locality. And this is pretty much everything you need to access in a cache, in a code, right? What does that mean? I can pretty much predict what you need, right? So if I can design some hardware to capture this locality, then it means that I am able to capture that 90% of the accuracy or even higher, right? So here is another proof of why it has locality. So here I use %p to print its address. And now I'm going to run a case where we have the matrix vector for 16 times and dump the memory address here. And as you can see, right, in the very beginning when we access A00, it ends with 330, and for B0 it ends with C30. And the next element in A01, because we are using a double number or integer 64, which is 64-bit number, means that is 8 bytes from the previous address. So you will see it's 338, which is 8 away, right? So it means that they are neighboring. And the same thing for the vector, right? So it's 30 and now C38, right? So that's spatial locality. And then if you pay attention to the next iteration, right here, you will see we are visiting B0 again, and the same address will come back, right? But however, it never comes back as in A, right? So in reality, this is, so the reason why I dumped that address for you is because I want to show you in reality, that's how we use the memory. And in fact, in a memory, there's not only your data, but also your instructions. And typically, in your code, in the very beginning, there will be a text section that's placing your instructions. And these instructions, they are typically by the program counter, in a program counter order, they are basically the statement by statement or instructions by instruction next to each other. So what does that mean? What does that really mean is that your code also has locality. And your code are basically more predictable than your data in a certain way that if you think about each neighboring statement, they are basically spatially located. And if you think about, we have the structure called loop, right? It's hard to imagine that you have a program that doesn't have a loop. You are executing the same block of instructions again and again. Isn't that temporal locality? Isn't that temporal locality? So what does that mean is that your code has locality no matter it's in code or data. And what does that mean is that most of the time, your program is just visiting a very small amount of data instructions within a given window. So a lot of people, they forget about a given window. They always think about, okay, if my data set is large, if my file is large, then I'm always dealing with a memory problem. I always have trouble with memory. But that's actually wrong. Because most of the time, your program is only visiting a very small portion of your code and data. So if you think I have terabytes of data set, there must be problem with my memory that I have to deal with. You are on the wrong direction. However, it's really important for you to see how our cache and processor behave on this small window of data and instruction that you have. But right now, one thing that we have to remember is that caching is possible because your code and data are so predictable in the normal behavior of an application. So now the question is that, can we design a hardware to exploit the locality? So in terms of the locality, right, we know we have spatial locality. So if we want to capture spatial locality, in the hardware perspective, what can we do? What can we do? So thinking about what ROPs do. What ROPs do? Okay, put things are likely to be together, close together, right? So that means that, it also means that every time when I fetch stuff into the caching, those stuff should come together, right? So the first thing we need to think about is that if we have spatial locality, right, is there a way every time when we do caching, we can put consecutive memory locations, data or instructions from consecutive memory locations all at the same time, right? And how about temporal locality? So to do that, right, every time your cache, when you cannot find something, you need to grab a few stuff, right? That's the concept of block, right? So now, if we don't do blocking, this is what happened, right? So in general, if your cache only cache the exact word that you're using, for example, here in this move instruction, I'm caching the address of 0040, right? And if that's the case, what I do is that I just cache the vector 0. However, if I am fetching, the next time I'm accessing 48, I have to go to the memory again, right? However, there is a more elegant way of doing this. First of all is that I divide my memory space into a set of blocks. So by blocks, it means that a fixed size chunk of virtual abstraction that I put in a whole memory space. So every time when I miss something in a cache, I grab everything within this abstracted block to my cache. So what happened is right now, if I'm missing this 0040, then instead of just fetching the data that's already on the 0040, I am fetching the whole thing that resides within the same block into the cache. So as you can imagine, if I can do that every time when I have a miss, the next time when I access a neighboring item like this 48, it's already in a cache. We don't have to go to the DRAM again. So it's more efficient, right? So the second thing, the second locality that we want to talk about is temporal locality. So as you can imagine, right, in a vector matrix multiplication example, we don't immediately reuse the same item, right? Like what I said in Rob's, I only buy another bottle of the sauce when I use all previous one, right? So turns out, in the meantime, you might have multiple different elements that you have access. So your cache also need the capability to keep multiple blocks at the same time. So what does that mean is that now, not only you have to keep one block, but also you have to keep another block in the cache, right? So two concepts, right? Caching is block-based. Every time when you have to access the lower level memory hierarchy, your cache always fetch data block by block. And the second thing is that your cache must have the ability of caching one block and another block and have a way to distinguish them, right? So now, if we want to keep the temporal locality, that's why we need to have multiple blocks, right? However, if we have multiple blocks in a cache, then the problem is, how do I distinguish each other? So in a cache structure, right, we need to have some additional identifier of each block to know who do I have in my cache. So that stuff is called tag array, right? So in your cache, there will be a tag array which would tell us which block is that. So now the problem is that what kind of identifier that I have to keep? What kind of identifier that I have to keep? So the answer is, first of all, why we need a fixed size chunk. Because it makes the identifier easy. In a way that if your block is always a fixed size chunk and your block is always consecutive, you would imagine it's monotonically increase in the memory addresses for data that you have in the same block. Agree? So if you dive into the detail of their memory address, you will find out for this fixed size partition, you can always find a common sequence in their memory addresses. You can always find a common sequence in their addresses. And because your memory address is monotonically increased throughout the whole memory space, each common sequence with the same block, they only appear once because you have a monotonically increasing in your memory address. Right? If you cannot think this through, probably you need to review your high school math or something. But agree with that, right? So for example, like this memory addresses, they are from here. And you can see for the same, within the same block, they always have the same prefix, right? So with that, what does that mean? When I fetch a block into the cache, I would also put this common sequence inside the cache as an identifier of the block. And because everyone in a block, they have the unique common sequence. They have the same unique common sequence. So only one set of the tag is good enough for everyone within the same block. Agree? Okay, so each block has a unique common prefix in their addresses, and that's what we would put. And the reason why we would need to partition them into fixed size chunk is because if you have the fixed size chunk, it makes sure that the common sequence is easy to identify. right? So this is, if you cannot think through this, go through this example, you should be able to notice that, right? So now, this is what we do, right? So we put a common address sequence prefix in each cache block, right? So saying that I have this tag array as well. So in your cache, typically we say the cache size, that's only for the data or instruction storage. But in fact, there are some overheads called tag. And the reason why we have tag is because we want to use this to identify who is in there. So now, how do we tell who is in there? First of all, there are a few additional structures we have to attach. First of all, every block not only have the tag, but also have a valid bit, which tells us if the data here is right now trustworthy. And there's also a dirty bit to tell if the data is being modified or not. So what happened with this whole structure is, first of all, if I have a memory address, I would separate the number of bits that is good enough to identify which byte in this block it is from within a cache. That's typically the least significant bits in your address. And then use this thing we call block offset to locate the starting location of the word or the size of the data that you are going to access. And then, so that's where we place the bit line or charge the bit line in your SRAM. And then we are going to compare the tag to see if there is a hit or a miss in a cache. So if we find someone with the same tag as what we want, that means that we found the data. And in this case, it's called a cache hit. However, if today I have another set of data code 4048, and I separate the block offset and the tag again, but I cannot find 404, right? So it's a 404 not found, right? So that's how and that's the case where we have to go to the lower level memory hierarchy to get my stuff if I cannot find a matching tag in a cache. So this sounds very complicated, but in the next lecture, I'm going to talk about how can we more efficiently knowing if your code is going to be a hit and miss or miss in a given cache structure. But before you leave the classroom, several important things that I have to mention. So as you are aware, this quarter we are going to use the testing center for the exam. And this is probably new to a lot of you. It's also new to me. So do me a favor. If possible, make a reservation to the test. And for the test, I have been asking the test censor regarding their rules. There's always a restriction that they can only release the available slots for you to take the test 2 business days before the period starts. And we schedule the practice time to be practice exam to be next week. So you can schedule the next week starting from today. And this is not mandatory, but highly recommended because no one ever used that. If you have never used that, you need to get familiar with how their computer feel and how stressful is it in that environment. Because one thing I love about that is that they have people proctoring for me. I don't have to do that by myself. And also, like what kind of equipment do they provide and what kind of stuff do they provide, right? So this is your duty to get there. And I put like 5 easy questions for you to answer in the practice exam. And but what does that mean is that if you give up this is just your decision. And it doesn't mean that I will accommodate any unfamiliarity of your testing environment. And it's also give you a chance to get familiar with how we make a reservation of the test. And this is important for your midterm and final. It's going to be always starting 2 business days before the starting scheduling period. And I know a lot of people, you guys want to schedule the exam late. So I do encourage people to start scheduling to early slots if possible. So either midterm. So for the midterm, one thing I would do is that if you schedule to an earlier start, you will have a smaller set of material to provide. If you schedule to like Wednesday or Thursday later in the week, you are going to have a larger set that you have to prepare, because it's easy for us to switch the question with the computer base. That's why I love it. And also reading quiz due next Tuesday. We have assignment 1 due tonight, and make sure that you always start the assignment early, and we don't have people working late in the night to answer your question. Like last Friday, I got the answer from like midnight on a question from midnight on Thursday. How can I answer you at that time, right? And we have already released assignment 2 and programming assignment 2. And if you want to practice that and working on a programming assignment 2, you are more than welcome to do that. And in fact, you are very welcome to do that. All right. Other than that, enjoy the rest of your day. I will see you next week.